Do you remember what a frequency distribution was?
Yes.
What was a frequency distribution?
That there's a range in values?
Well, sometimes we broke it down into classes, so we had a range of values. But what basically is it?
How many times n occurred?
Yeah, so it's just a chart, right? A chart showing how many times each result occurred. That's it. Or each data value occurred in a set. Okay, so what do you think a probability distribution is going to be?
Something that charts the probability of something occurring.
Yep. So instead of telling me the number of actual times it occurred, it's going to tell me just the theoretical probability that it occurred. That's all it is. Nothing complicated about it. So we're talking about a probability distribution, which gives a probability for each value of a variable that is determined by chance. We're going to be talking about whether an outcome is unusual in the sense that it's not likely to occur by chance. I'll remind you what that means in a minute. I do want to go to the slideshow version of this guy. Okay, so consider the scenario that there are 3 siblings in a family. Remember what do I mean by the sample space for that? Yes, GGG, BBB, all the possible outcomes for gender is what we were always talking about. So the sample space was BBB, BBG, BGB, all the different possible birth orders of male and female. These are the only things that can happen. Now what we're going to do is to construct a probability distribution, but for a particular outcome. So we call X a random variable and we assign it a certain value. So in this case, let X be the number of boys in the family. This random variable has how many possible values, or which possible values, I should say. So for example, in the first outcome of the sample space, what's the value of the random variable X? 3. There were 3 boys, right? In this outcome, there were 2 boys. In this one, there were 2. In this one, there were 2. In this one, the random variable X would have a value of 1, 1, 1, and 0. So what are the possible values of the random variable X if it represents the number of boys in the family? 0, 1, 2, or 3. Okay? This is just some terminology. Random variable is just representing different outcomes. We tell you what the random variable represents, in this case, the number of boys in the family. So you figure out what are the different possible outcomes, how many boys. Okay, we're going to go ahead and before we construct the probability distribution for this, which remember is just a chart, what is the chart going to have on it? The probabilities of these things happening. The probability that the random variable X is 0, 1, 2, or 3, which sounds scary, but all I'm saying is let's write down the probability of getting no boys, the probability of getting 1 boy, the probability of getting 2 boys, and so on. So what's the probability? This is the notation we use. Capital P with the parenthesis. Okay, X equals 0. Wow, that looks very weird and abstract. What is that really saying? The probability of getting 0 boys. X means number of boys, so we're just saying probability of 0 boys. So you tell me, how would I write down that probability? Okay, so it only happened once out of the 8 different events in the simple events in the sample space. So that's equal to the probability of getting girl, 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 right? Which is 1 out of 8. Good. How about the probability of X being 1? So let's translate that into something more understandable. What are we saying? What's the probability of 1 boy? That's it. That's all that means. So you tell me.
3 out of 8.
3 of the outcomes, yeah. So that's the same as saying the probability of getting boy, girl, 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 boy, girl, or girl, girl, boy. 3 different outcomes out of the 8. You don't have to write that second part down. You can just write 3/8. What's the probability that the random variable x is equal to 2?
3.
Okay. There were 3 outcomes equal to 2. So 3 out of 8 again. And what's the probability that x is equal to 3?
1 out of 8.
Yeah, only one way that can happen, all 3 boys, 1 out of the 8. So those probabilities that we just found are all the probabilities for the random variable x. In other words, we've found the probability for each possible value of the random variable, and all that a probability distribution is that you put that in a chart. Okay, so you put an x at the top of one column. Remember, this x was the, quote, random variable that represents the number of boys out of 3 children. And in the next column over, we have p of x, the probability of x happening. Probability of 0 is 1/8. I just copied those values from what you just did on the previous screen. You can sometimes see it in a fraction form. You can sometimes see it in a decimal form. You shouldn't round off unless you're told to do so. That's a probability distribution. Do we notice anything about the values in the probability column? What should they add up to?
1.
Yeah, why should they add up to 1?
Because 1 is that it's possible to happen.
Guaranteed, right? Remember, the probability of 1 means that it's guaranteed to happen. And it's guaranteed that you're either going to have no boys, 1 boy, 2 boy, or 3 boys, right? And notice that I said or. So 0 boys or 1 boy or 2 boys or 3 boys. When I use the word or, I have to add the probabilities together. So if you add up all those probabilities, you get 1. And if your probability distribution does not add up to 1, then you got a problem. You did something wrong. Okay, so this should always add up. If you add up all the p of x's, you should get 1. Remember, our sigma means the sum of the probabilities should add up to 1. Okay. All right, you're going to hear this terminology. We're not going to, it's not going to be a huge part of what we're doing. You can usually fudge it, but it's good to know the difference between a discrete random variable and a continuous random variable. So discrete refers to something that we call countable. So like we just had on the previous slide, we had 0 boys, 1 boy, 2 boys, 3 boys, or 4 boys. That's called a discrete random variable, where there are individual finite values where you can see that halfway between 2 of the values, there's not a third. For example, what's the number of boys between 2 and 3? 2.5 boys? No, that doesn't make any sense. So it's discrete because it's separate. There's not a continuity between the numbers. On the other hand, there are continuous random variables that have infinitely many values between any 2 values. So between any 2 values, there's a third with no gaps or interruptions. So you're going to get a bunch of decimals for, like, I don't know, weights of children, right? If any of you have kids and you've gone to the pediatrician and they show you that chart where's your kid's weight fall on the chart there, right? So that's a continuous random variable. Okay, this was a discrete random variable. That's what I was just mentioning that we just looked at. We will deal with continuous random variables differently because obviously we can't list an infinite number of them over there. Okay. So what are the requirements for something to be a probability distribution? So you're going to have possibly a question on your test where it just gives you a chart and asks you, could this be a probability distribution? And so these are the conditions. First of all, and this is a little out of whack here. Hold on. That should be that should be here. That should be here. All right. There is a numerical random variable x, and its values are associated with some probabilities. Okay? It doesn't necessarily have to be 0, 1, 2, and 3. It could be other values, but we have a list of x values associated with probabilities. The sum of the probabilities has to add up to 1, like we just talked about. And also, obviously, since these are supposed to be probabilities, each individual probability should be between 0 and 1. So if I gave you a probability distribution that looked like x, p of x, if I asked you, is this a probability distribution? And you had 1/2, 1/3, 4/3, okay? Is that a probability distribution?
No.
No, because
4/3.
4/3 is bigger than 1. Okay, so that right there is a problem. And you could also justify your answer by saying that this adds up to something other than 1. The sum of the p of x is actually whatever 5/3 plus 1/2 is. 5/3 plus 1/2 is 10/6 plus 3/6, 13/6, which is also not equal to 1. So if that's violated, then it's not a probability distribution. So be prepared to answer a question like that. Another thing that could make it not a probability distribution is if these were not numeric values here. Okay. It has to be a numerical random variable. Okay. Do you remember our histograms that we made from our frequency distributions? So on the histogram, each bar represented the number of times a particular outcome occurred, a particular value appeared in the data. We're going to have probability distributions where the bar is just the y-axis here, the vertical axis is just the probabilities. So each one of these bars tells you how likely the outcome is. I would like to point out that we've actually seen probability histograms before, but we called them relative frequency histograms, because what is a relative frequency really? You take the number of times an outcome occurs and divide it by the total number of outcomes. That's really a probability, isn't it? So F over n, the frequency divided by the total number of values, is your approximate probability, although we are looking at theoretical probabilities, and back in chapter 2, I guess it was, and 3, we were looking at data values, so we used actual values, not theoretical values. Okay, so how do we deal with continuous random variables? The probability of the value of a random variable being in a particular range we can represent by the area under a curve. So what I mean by this is, for example, if we wanted to know the probability that our random, let's say this number line, I don't know what it represents, but let's say right here, this is the value negative 0.5 and this is the value 0.5. What this is saying is that you look at the area under this drawing. This shows that, for example, if 0 is right in the middle, that occurs the most with the most likelihood, the greatest probability. But it also tells you specifically if you find the area between negative 0.5 and 0.5, and that area under the curve is 0.359, that tells you the probability of a value being between negative 0.5 and 0.5 is 0.359. So what we do, I guess what I'm saying is we can't list we can't list each individual value because we have an infinite number of them. So the way we deal with it is we draw a representative graph and we use the areas under the graph to represent the probabilities. Notice that since all the probabilities have to add up to a total of 1, the area under one of these probability distribution graphs is going to be 1. The total area will be 1. And if we find the area under a little piece, like we did with the empirical rule, remember? This is a very similar thing. You're finding the area of a little piece, but this time it represents the probability of getting that value, or a value in that range, I should say. Okay. Recall that we learned in the previous chapters that the population mean, mu, was the sum of all the products of the data values times their frequencies divided by n, the total number of data values. Do you remember that formula? Okay, how do you find an average? I just want to make sure everybody's still on the same page. How do you find a mean? You add up all the data values, right? And divide by the number of data values, yes? So why don't I just say add up all the x's here? Because in a frequency distribution, each data value doesn't appear the number of times it is in the set. You have the data value and then you have the F column that shows how many times it appeared, right? So you have to multiply, like when we did our grade point average, you have to multiply the data value times its weight, its frequency, and then divide that sum by the total number of data values in the set. I'm just reminding you of this because we're going to look at it in the context of probability, so that the formula will look different, but it'll actually be the same thing. We found population variance by taking the sum of the squares of the deviations from the mean times the frequency. Do you remember that big messy formula? And dividing it by n, or if it was a sample variance, we divided by n minus 1. Do you remember us working with that? And then the standard deviation was just the square root of that formula. Okay, so I want to point out that in each of these formulas, we have an f over n. You see that f over n that appears there? And what is f over n?
Probability.
The probability. F over n is always the probability. So we actually, when we're talking about probability distributions, we can use the information in a probability distribution to also find the mean, the variance, and the standard deviation, because all we're going to do is we're going to replace that f over n with the probability. And so the formulas adjusted for that are going to look like this instead. So the mean becomes the sum of all the x's multiplied by the probability of getting that x. Right? Going back a slide, we had the sum of x times f divided by each one of those divided by n. So instead, f over n is just the probability. So you don't have that fraction anymore. You just have x times p of x. P of x really is just f over n. And then for the variance, same thing, replacing the f over n with p of x. This new formula appears, and replacing it in the standard deviation, you just take the square root. So you're going to need to know that if you're given a probability distribution and I ask you for the mean, this is the version of the formula that you're going to use. So given a probability distribution, you have to use these versions of the formulas. So let's try it. Okay. It says the following table describes the probability distribution for the number of girls in 2 births. Number of girls in 2 births is our random variable x. Is it a discrete random variable or is it a continuous random variable? Discrete, very good, because it has individual specific values, not a range of values. So how do we find the mean, the variance, and the standard deviation? Well, we're going to construct the frequency distribution, and that just means finding the probability of 0 girls, 1 girl, and 2 girls, right? Because it's out of 2 births. So what is the sample space for 2 births? Girl, 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 boy, boy, girl, and boy, boy. All right, so when in this box, what I'm saying is find the probability that x equals 0. Find the probability of no girls. So how do you do that?
1/4.
Okay, the only way that can happen is 2 boys. That's 1 out of the 4. How about the probability of 1 girl? 2 out of the 4, good. And the probability of 2 girls? 1 out of 4 again.
Which equals 1.
Okay, I wrote those as decimals just so that it's easier to work with. 1/4, 1/2, and 1/4. Okay, now what was the formula? How do we find the mean? Remember, those formulas are telling you a procedure, right? X times P of X and add it up is what it said. So I'm going to need an X times P of X column in order to find the mean. And to find the standard deviation and the variance, first the variance, I'm going to need an x minus mu squared times P of X column. But let's focus on finding the mean first. Okay, x times P of X, what would that be for this first row here? 0 times 0.25 is 0, yes. And then 1 times 0.5 is 0.5, and then 2 times 0.25 is 0.5. And supposedly, we get the mean by just adding these 3 values up. The sum of the xp is the mean. Sum of the xp of x is the mean. So would it make sense for the mean number of girls out of 2 births to be 1? That kind of sounds reasonable, doesn't it? Out of 2 births, on average, to get 1 girl, because it balances out, right? You've got the cases where you get 1 girl, and then you've got the cases where you get no girls, but that's balanced by the cases where you get 2. So it averages out to 1 girl per family. All right, now that's the mean. So see how easy that is to find the mean when you have the probability distribution? You just multiply the number times the probability, and you get, I should say, you multiply the discrete random variable times the probability, and you get the xp of x column added up, and you get the mean. Okay, how about the variance? So in order to get the variance, we need the mean, but we just found that. So this is the mean of 1. So for example, this first cell here in the far right column is going to be 0 minus 1 squared times 0. So what's that going to be? Just 0. This one is going to be what? 1 minus 1 squared times 0.5, which is also 0. And the third one, we would have 2 minus 1 squared times 0.5, which is going to be 1 times 0.5, which is 0.5. Okay, so the variance means adding up all of those. So what should the variance turn out to be then? 0.5, okay. Remember, our notation for variance is sigma squared, because the relationship between the standard we don't actually have a variable for variance. We just say, okay, well, it's this it's the standard deviation squared. All right, and then, so to find my standard deviation, I do what?
Square root.
Take the square root, that's right. Do I have that on here? Okay, the square root of 0.5 is 0.707. Now, here's the $1 million question. What the heck does that mean? Do you remember what a standard deviation represents?
Number of distances away from the mean.
Yeah, so you want to think of the standard deviation as being the amount a typical piece of data deviates from the mean. It's a way of measuring how spread out the data is. It's also a way of giving a position of the data within, it can be used to help us find the position of data within a data set. So that's why we find standard deviations. All right, now you can actually use your TI-30X2S to find the parameters of a probability distribution. So let's do that for this probability distribution. We're going to cheat, okay? We're going to pretend, for the calculator's benefit, that there are exactly 100 data values. And so we're going, 100 data values in the set. And so since, for example, the data value 0 occurs a quarter of the time, we're going to pretend that there were 25 of those. So I just moved the decimal 2 places over. Do you see that? Okay, and then since the data value 1 occurs 50% of the time, has a probability of 0.5, that would mean 50 out of 100. And I'm doing this because your calculator does not want your frequency to be a decimal. So you remember how we were able to put in a frequency distribution into your calculator and it found the mean and everything for you? So in some cases you can cheat on this probability thing, probability distribution thing. Just think of it out of 100. Tell your calculator that these are your data values and these are the corresponding frequencies, and do the calculation like we normally do. Remember we did the stat var thing, and we went to arrowed over to get our mean and our standard deviation. Then you just square the standard deviation to get the variance. Okay, so that's how you can cheat on that one. All right, so just as this is out of your textbook, it's just kind of an overview comparing what we did in chapters 2 and 3 to what we did in chapter 4. So in chapters 2 and 3, we used frequency distributions to analyze how many times data values occurred. Then we found the mean and standard deviation from that. In chapter 4, we're finding the probabilities, and then we're using a probability distribution, but in the end, we also are going to find the mean and standard deviation. Now, big difference. You should get similar outcomes, but in chapter 2 and 3, we were looking at actual data sets where we actually collected the data, and usually the data in your data set is not going to end up aligning perfectly with your theoretical probability. So you're going to see that, for example, here, the mean of the data set, the sample data, was 0.9, but mu, the mean of the population based on the theoretical probability, turns out to be 1. But it's going to be very, very close. All right. Range rule of thumb. So I believe we've seen this before in a different context. According to the range rule of thumb, most values should lie within 2 standard deviations of the mean. Again, standard deviation is the amount a typical data value differs from the mean. So you're going to get most of the data values within 1 standard deviation of the mean, but you're certainly going to get the vast majority of the data values within 2 standard deviations of the mean. So if we want to figure out if a particular value is unusual, like not likely to occur randomly, we are looking for values that are outside of 2 standard deviations away from the mean. How do we represent that? Remember, mu is the mean, and then we're going to add to that 2 times the standard deviation. And that, if you imagine a number line where we have put our mean value on the number line, what we're going to get there is, if this is one standard deviation sigma and this is another sigma, the value we're looking at here is the mean plus 2 standard deviations, mu plus 2 sigma. But we're not saying that most of the data values are between here, the mean and that. We're saying within 2 standard deviations. So you also could be with, go down as low as mu minus 2 sigma. And you can see why we get most of the data values and take up most of the graph there. So if you're asked to determine if something's unusual, you need to remember to calculate the maximum usual value, mu plus 2 sigma, calculate the minimum one, and just see if your value lies between them or outside of them. So here's an example. We found for families with 2 children that the mean number of girls was 1.0, and when we calculated the standard deviation, it turned out to be 0.7. Use those values to find the maximum and minimum usual values for number of girls. Okay. So the maximum usual value is just mu plus 2 sigma, so that's 1 plus 2 times 0.7. 2 times 0.7 is 1.4. So 1.0 plus 1.4 is 2.4. Minimum usual value is mu minus 2 times sigma. Just a quick little reminder of order of operations here. You have to do the multiplication before you do addition or subtraction, right? So make sure when you're plugging this into your calculator, you do not type in 1 minus 2 and then times 0.7, because you could confuse your calculator. So be careful with how your calculator interprets standard order of operations. So you subtract 1.4, you get negative 0.04. So any data value between a negative 0.4 number of girls and a 2.4 number of girls would be considered a usual value. It's not really very insightful in this case, but we're just using the numbers, because what is that really saying? Oh, it would be unusual when you have 2 children to get less than 0 girls or more than 2 girls. So of course that would be impossible, actually, more than unusual. Okay, would it be unusual though for a family to have no girls? How do we figure that out? The answer is no. How did I come to that conclusion though?
Because it can go as low as negative 0.4.
So what does, what does no girls mean? 0 girls. So what are we really asking? Is 0 between negative 0.4 and 2.4? Yes. So it is not at all unusual for a family to have no girls. Okay, so that was a way of using standard deviations to determine if probabilities are unusual or outcomes are unusual. You can also use probabilities to determine, I think we've talked about this before. No, actually we haven't, because in this case, in order for something to be unusually high, an unusually high number of outcomes of a certain value, there has to be that the probability of X or more is less than or equal to 0.05. And in order to be unusually low, just jot this down, and I'll explain in a context of an example better. Unusually low means the probability of having X or fewer is 0.05. Okay, so let's take a look at an example. Here we have the probability distribution for, again, the number of girls in a family with 2 children. And the question is it unusual for a family to have no girls? in the previous example, we decided using the range rule of thumb that it was not unusual for a family to have no girls. But now we're going to use this other version of that criteria. So we can look at probabilities, and we can determine if it's less than 0.05 of a chance to have a value that extreme, then you would say it would be unusual. All right, so to have no girls, we have to look at the probability of having 0 or fewer. Now that's silly in this case, okay? But in the cases where we have a lot of other possible, like maybe 10 children, and we want to know, is it unusual to only have 2 girls out of 10 children? We would have to say, in order to be unusual, you'd have to add up all the probabilities for having 2 or 1 or 0. Anything that extreme or more extreme, we need to know the sum total of that probability. Why? Because to get when you look at the probability of one particular outcome, like we saw a slide earlier in the semester where we talked about, okay, something like there were 600 children born in a hospital one day, right? Would it be highly unusual to have 288 of them be girls? Remember that? And we said that wouldn't be an unusual outcome to have that happen. That could certainly happen. It's close to 300. It's within the realm of reason. But if you were taking bets on how many of the 600 babies were girls, would your chances, if you bet 288, would you have a good chance of winning?
No.
No, because you could have also had 287, 286. There's 600 different possibilities that you're choosing from. So it's a 1 out of a 600 probability. It's a very, very small chance of that happening. But if you say, is it unusual to have only 288 of the babies be girls, what you do is you add up that or anything more extreme. So you add up the probability of 288 plus 287 plus 286 and so on. And what you get is 288 out of 600 probability of having that value or something more extreme. You see what I mean? So it's not unusual to have a value in that extremity, but it is unusual to have exactly that one value. So when we're looking for unusual values, we always have to consider, as that extreme or worse, would that be likely to happen or not? So anyway, on this chart, probability of 0 or fewer, well, that's only the probability of 0 in this case. So the probability is 0.25. So is that unusual to have no girls? Remember, it's only unusual if we have 0.05 or less. So you compare 0.25 to 0.05 and you say, well, 0.25 is greater than that. So no, it's not unusual to have 0 girls. Okay, another thing in this section that we need to understand is the expected value of a discrete random variable. Okay, luckily, there's nothing to learn here except the name, because the expected value is just the mean, right? I mean, what we expect is for the typical data value to occur, which is the average, the mean. Okay, so whenever you're asked, given a frequency distribution, what's the expected value, you're going to find the mean. And remember, when you're finding the mean of a probability distribution, you're going to just multiply x times the probability and add them up. This is really just the mean, mu. So it's nothing new, but it has a different name. So when you see those in your homework, remember, expected value just means mean. Okay? All right, trucking right along here. Do you guys need a break before we continue? Yes? Okay. Let's take a 4-minute break.